Okay, so in the last class, we were discussing about 2D unsteady heat conduction. Equation for numerical solution. So while doing the discretization using implicit method, we came to know that finally we have to solve a matrix of using BTCS. This gives a matrix of this form 2 gamma y, gamma x 0 minus gamma y. So this is a pentadiagonal sparse matrix. And we designated this in terms of single index notation. By doing this, we may save a memory in a computer. Okay, 2D array may take more space, that is rather than 1D array. So this is the equation, and we say about this matrix is a sparse matrix. Okay, it is also pentadiagonal. You have first diagonal, second diagonal entries, third diagonal, fourth and fifth diagonal entries. So pentadiagonal. Pentadiagonal means it is also called as banded matrix. So pentadiagonal is a band. Okay. Tridiagonal is also band. So pentadiagonal, tridiagonal, these all matrices are called banded matrix. So if you use Gauss elimination, for example, so if you use Gauss elimination to solve this, Ax is equals to B system, okay, then Gauss elimination will be very poor, okay, for such system. Why it is very poor? Because many times these zeros, by doing this operation in G, Gauss elimination, some zeros may become non-zero values, and we might not be, getting a sufficient iterations or after some sufficient operations, the required uh, matrix. Okay, so reason for this because all zeros within the band within the band becomes non-zero during the elimination process, during the Gauss elimination process. See, I have observed that many students, they are not writing this Gauss G capital, Jordan J capital. Please write name first letter of the name capital always. Since you are masters and PhD students, please take care of that. individually, term by term. And this may be cost, it may be cost incurring. So if you go for a 3D system, such same problem will be for the 3D system. And, so uh, similar may be the case. Similar is the case for, this is a 2D problem, but similar is the case for 3D. So in and all, Gauss elimination method is ineffective. Okay, you should not use. So we should look for, so we should look for iterative methods. Iterative methods. So since we said Gauss elimination, even your TDMA or pentadiagonal matrix algorithm, they also will be very poor. Okay. They may be very good compared to Gauss elimination, but the process involved in TDMA and pentadiagonal matrix algorithm, they are based on the Gauss elimination process. So this problem may not be general in case of TDMA method. So for general cases, we should look for iterative methods only. Okay. And in iterative methods, we solve with, we start with guess solution. Okay. As you already said, seen in your exam also, you have to start with a guess solution and keep on and keep on and keep correcting, keep on correcting the solution till it converts to a correct solution, till it converges to correct solution. Okay. So one of the most popular iterative method is most popular in the sense most efficient also. Popular iterative method is the Gauss-Seidel method. Is the Gauss-Seidel method. Okay. Particularly for finite difference method, particularly for the finite difference methods, FDM, and finite volume methods, and the finite volume methods. FVM. Okay. So we should look for Gauss-Seidel method. Okay, and this is the most we'll be using. Okay, Gauss-Seidel method. And we look for a matrix-free version. Okay, matrix-free version of matrix-free method. We will not solve any matrix in, we will not do like TDMA. Okay, we will not supply any matrix or like that. So in that sense, we are not doing any particular uh, process of supplying the matrix and doing operation on it, finding its inverse like that. So how do you do it? So in Gauss-Seidel method, we as to start with, from a theoretical perspective, we essentially follow this, as we said, right? So this A will be our n by n matrix. Okay, n by n matrix. X will be a column vector. This will be a column vector. Column vector of size n, and B will be another column vector of size n. Column vector of size n. Okay. Now here, what is the size of this matrix? In a single index notation, what is the size of the matrix? Anybody? What is the size of this matrix?
It is n by n, sir.
It is n by n. Means if you have these many grid points, okay, we have these many grid points, means up to this you should have these many numbers. Okay, if this is the n, this is n, and in y direction also you have another n, then it should be n by n. Okay. Similarly, this will be total this n elements, n by n elements, n elements. Okay. This will be all 1, 2, 3, 4, this all total n by n elements. Okay. Okay. So this is the structure of that. So what we do, as we said in all iterative method, rather than we say that we solve for a guess value. Okay. So for any guess value, guess solution, for any guess solution, we can define a residual. Okay. What is residual? Residual is nothing but R is equals to whatever is right hand side, B minus A, that matrix, and our guess solution. Okay. X is a exact solution, so X should be equal to B. So in that case, if X is equals to Xg, then residual should be 0. If Xg is X, then residual Rg, then Rg should be 0, isn't it? So that is what we are trying to do. First we guess, we estimate the Rg, and we again calculate some new value of xg such a way that this Rg tends to become 0. Okay, we initiate with the guess value, find out the Rg residual, and again correct the guess value such a way that Rg becomes 0. What does it mean? It means that x, which is a final solution, should be is equals to the guess value plus a correction value. Guess value plus correction, this will make the exact. Okay, this will make the exact and the residual will be 0. We want when the residual is 0, that is nothing but the final solution. Okay, if residual is 0, it means that we approach the solution. So that is the process we are going to follow here. So what differences we see in the iterative methods and how the iterative methods are different. So to see that, we now substitute this x into our previous matrix, and we can write, if we substitute in x, so we can write like xg plus x prime is equals to b. Okay. If you now again do some xg plus ax prime is equals to b. Okay. Now ax prime is equals to b minus axg, and this b minus axg is nothing but Rg. Okay. So from this matrix we got the correction the equation for correction column vector. Okay, correction solution, solution correction. This is the correct solution, this is the correction, and if we find a correction, then we can add to the guess value that correction, and you can find a new value and check whether residual is falling, 0 or not. If not, then again you assume the guess value as this value as guess value. Are you getting this? So from this, what you do is, I'll just write it here. So from this equation, obtain x prime. Okay. Estimate x is equals to xg plus x prime. Okay. If Rg is equals to b minus ax is not equals to 0, again xg is equals to x, else xg is equals to x, and repeat 1, 2, 3. One, two, three. Else x prime x is equals to x is a solution, not x prime. Xg is a solution. Okay, but you see again here, if you want to calculate x prime, you have to do matrix calculations. Okay, now this is same as doing this process. Rather you do ax is equals to b, or you solve ax prime is equals to b. So what is an advantage? Ax prime is equals to Rg. What is an advantage? It is the same type. So whatever the efforts required to solve Ax is equals to B, the same efforts are required for Ax prime is equals to Rg. So in order to avoid this, okay, in order to avoid this, this equation B, this equation A, solving equation solving equation P is similar to solving equation, we get the solution, okay, but the method of now the worry is about method of solution. Equation A and it is as difficult to solve as X is equals to B. Is equation B, okay. So why it is difficult to solve? Suppose you want to find out X prime from this. So X prime means is equals to A inverse and then RG. So finding A inverse itself is a difficult activity. We do not want to calculate A inverse. So what do we do? So the crucial step in, therefore, the crucial step or the important step in iterative methods is to modify is to modify A. Okay, this is very important to remember. We modify A itself. Okay, so that, and we have already done this, okay, but so that A approximate X prime is equals to RG or B, you can say, can be, is much easier to solve, much easier to solve. Compared to AX is equals to B. Okay, and all the iterative methods differ differs in the way A approximate is defined. Okay, or approximated. So for example, if you go for a Jordan method, Gauss-Jordan method, which is also called as Gauss-Jordan method, so in case of Gauss-Jordan method, A approximation will be equals to A say A11, A22, A33, ANN. Okay, and all other values will be 0. You check this in your Gauss-Jordan method. Have you done like this? Okay, so you will see that you have done like this. And in case of the Gauss-Seidel method, our A approximation was the lower triangular matrix. So A11, A21, A22, these things were there. Okay. Similarly, AN1 and rest of the terms up to ANN. And all other above diagonal terms, they were above diagonal terms. So here there were terms, here there were terms, here there were terms, here also there were terms. Similarly here, and all other terms becomes 0. This is a specific form we get in Gauss-Seidel. And in Gauss-Jordan, we get only diagonal matrix. Here we get lower diagonal matrix. But we do not need to construct such a matrix. Okay. But we do not need to construct such a matrix, such matrices. To use the iterative methods. So how do you do this? So how do you do this? So we mainly need to know, we mainly need to know the residual. This is very important. Okay, we need to know the residual, and residual is defined as 3 lines means definition. Right hand side minus always left hand side. Remember, right hand side minus always right hand side. Okay, so by this we need not to know the matrix A. How do you do this? How do you calculate residuals? So for example, in our case, for example, for BTCS, our equation was of this nature: gamma y t I j minus 1 to the power n plus 1 minus gamma x t I minus 1 comma j n plus 1 plus 1 plus 2 gamma x plus 2 gamma y t I j for 2D problem, as we have already seen, n plus 1 minus gamma x in a double index notation, I plus 1 comma j n plus 1 minus gamma y t I j plus 1 n plus 1 is equals to t I j n. Okay. Now we would like to write a residual for ij. This is the equation for ij. This is the equation for ij. For ij, this is the equation, isn't it? So similarly, residual for ij has to be written down. So what is the residual for ij? That has to be mentioned here. So residual for ij is right here, residual, and we denote Rij, residual by Rij. Rij. Rij is equals to, what is the right hand side? This is the right hand side. So you write that equation, right hand side Tij n minus left hand side, all the terms in the left hand side, minus of this, minus of minus. So it goes to the right. Minus of left hand side. So minus minus plus. So this minus of this minus, this will become plus. So gamma y Ti j minus 1 n plus 1. Similarly, this will be plus gamma x Ti minus 1 comma j n plus 1, and plus of minus will become minus plus of 2 gamma x plus 2 gamma y Tij. It is very easy, isn't it? Just left hand side minus right hand side. So we calculate residual like this. Then what do we do with the residual? We'll see. Let me write this I j plus 1 n plus 1. So this is the residual. Now what to be done with the residual? Along with this, we will also note the central coefficient, okay? The diagonal element, okay? Central coefficients. Central coefficients. It is also called as coefficient of diagonal element. Coefficient of coefficient of coefficient of diagonal element. Diagonal element. Okay. What is the diagonal element in this case? Anybody? What is the diagonal element in this case? What is the diagonal element? Anybody? Hello?
Sir, the Tij.
Yes, Tij is the diagonal element. Diagonal element is the Tij. Very good. Tij n plus 1. Very good. So central coefficient is represented as AII. Okay. We'll say coefficients represented by AII, Ij, sorry, Aij is equals to, what is that? Central coefficient is 1 plus 2 gamma x. This, from this equation, not from this equation. Otherwise, negative will come and everything will get destroyed. Okay, disturbed. Plus 2 gamma y. This is Aij. Okay, so what do we do is, so we'll again see by some example. So say for example, you have a Gauss-Jordan method. Gauss-Jordan. So in case of Gauss-Jordan, you know that you have approximate matrix which represent like A11, A22 and ANN. Okay, there will be some diagonal entries and all are zeros here. And we solve for x prime, say, and we have residual r here. So in this case, x prime is always is equals to r divided by a I, isn't it? Suppose xi is there, then you have this aij, r aij, isn't it? Xi a r divided by aij. You see, this sum xi is there, a11. So solution is x prime is equals to r divided by a11 in this from first equation. x1 is equals to r1 divided by a11. Similarly, x2 will be equals to r2 divided by a22, and xn will be equals to rn divided by ann. So this is the form, and we have already said that whatever the guess value we have xg, in to that we add this correction to get the solution. Okay, so finally what we are going to do is we are going to only calculate these things. We will calculate x prime, we'll add to xg, and we'll calculate x and see whether the residual is 0 or not. That is the procedure we are going to follow without considering any matrix. Okay, the matrix is considered only in this formulation, but later on there is no need to define the matrix in any way. Okay, so how I can write now in terms of temperature? For example, suppose the x is a temperature, then I can write temperature T ij, okay, Tij, and at n plus 1, and this is the new solution. Okay, this is, we will say, new solution. X is a new solution which will be equals to the Gauss solution. Okay, this is a Gauss solution Tij n plus 1. This is the Gauss solution plus the x prime. X prime is R. R is a residual, isn't it? Here R is a residual. For the correction x prime, Rg is the residual. So R ij divided by A ij. Means AII you can say. Okay, here J should be equals to I. Then only Aij. So it is better to write AII only. Otherwise, you will have to define J is equals to I. So AI. Okay, you got? So the first time this can be a Gauss value. So if I write like this, this can be a Gauss value. Okay, and you can say that Tij n plus 1 is equals to some 0. So at first time, this Gauss value, Tij Gauss value will be a 0, and you will get some new value. So I can write this equation such a way, in this manner, so that next time I get another new value with the old value, but the meaning should be same. So I can write the same thing Tij n plus 1 like this, isn't it? New only. So rather than saying this, rather than saying guess, I'll say T new. It is just nomenclature. T new is equals to 0, and first time. So this is not going to be calculated by, the terms, only values will be substituted of this in any programming language. These values will be assigned to this. These values will be assigned. Okay, that is the rule. Right hand side is always assigned in the left hand side. So whatever the first value is there, first it will be assigned here. So I can write this as new only, T new. The Gauss can be written as T new. The Gauss can be written as T new. And rest of the things can be kept same. Okay, so this doesn't change the meaning, isn't it? So I can write Tij n plus 1 new is equals to Tij n plus 1 new plus Rij divided by Ai. This is going to give you Tij. Okay. So this is a definition. So now you need not to write a T new. So we can write Tij n plus 1, and this can be defined. This can be defined as Tij n plus 1 plus Rij and Aii, which is nothing but equals to, for our BTCS scheme, Tij n plus 1 plus Rij will be equation Now we obtained here this equation. This equation you will have to write here completely. Okay. Rij divided by AII. AII is 1 plus gamma x, 2 gamma x, 1 plus 2 gamma x, 1 plus 2 gamma x plus 2 gamma y. This is the thing you have to write. And Rij is this Rij. You have to write completely this Rij here. This Rij. So by this way, you keep on calculating these values. Okay. And these values has to be calculated for, okay. This is to be done for, this is to be done for interior as well as boundary points, or interior as well as boundary points. Okay. For boundary points also you have to find out the residuals. For example, suppose the boundary condition is like del t del x is equals to 0, and if you use the backward difference method, Tij minus Ti minus 1j, okay, n plus 1, n plus 1, n plus 1, n plus 1, delta x is equals to 0. This gives you the Tij n plus 1 is equals to Ti minus 1 comma j n plus 1. Now here residual Ij will be equals to this right hand side Tij uh, uh, Ti minus 1j n plus 1 minus this Tij n plus 1. This is your residual for the boundary condition equation. And AII for the boundary condition will be this central coefficient, that is nothing but 1. Okay. So you have to define like this in all these equations. This is called as iteration sweep. Okay. This is called as iteration sweep. Iteration sweep. This is
Sir,
called as
sir, how that AII became 1, sir?
what is the central coefficient for Tij? This equation.
Yes, sir. Okay, sir.
AII is a central coefficient. This is the residual. Okay. Again, I will write here. This is a residual and this is a central coefficient. Okay. Since we are using this equation, we need this Rij and AII. So similarly, for this equation, the Tij n plus 1, Tij n plus 1 will be equals to Tij n plus 1 plus this Rij, this Rij plus this Rij divided by A11, that is nothing but 1, and this Rij for boundary. These are for interior. So this will be for interior, isn't it? Because this was for interior and this will be for boundary. Similarly, there will be other boundaries. So you will have to find out for other boundaries what are my Tij. And when you write this Tij, at that moment you know that what is I and j, isn't it? So you will be writing. If it is a left boundary, then right boundary. Accordingly, Tij values will appear there. Okay. If it is a left boundary and j is varying, then it will be T is T1j. Okay. And accordingly, Tij, this will be T, if it is 1 minus, so T, or like that, you know. So this should be a right boundary condition. if you are taken backward. But you understood the meaning, what I'm trying to say here. Okay. So based on the problem, you should be in a position to find out Rij and Aii for that particular equation. And this is called an iteration sweep. And this iteration sweep, this iteration, this iteration sweep have to be continued till the RMS value, okay, till the RMS value, RMS, root means square, RMS value is less than some epsilon, where epsilon is a small number, where epsilon is a small number nearly equals to 0, number nearly equals to 0. So in case of the computers, 10 to the power minus 5, 10 to the power minus 6, 10 to the power minus 8 can be thought of close to 0. Okay. So you have to specify some number so that you can stop. And what is that condition you can apply on the RMS value is that you take the square root, you take the Rij square. Okay, whatever the Rij you are calculating, you have to sum all the Rij. Okay, sum of all Rij. Sum of all Rij means interior plus all the Rijs that are coming from the boundaries. And divide that Rij with the n grid points. Total grid point, n by n, total grid points. Okay. So if this value, if this RMS value is less than 10 to the power or equals to 10 to the power minus 5, then you stop. Okay. So this is a stopping criteria. Okay. This is a stopping criteria. Stopping criteria. There are many types of stopping criteria. This is root mean square. Okay. Root mean square. So we have taken mean here by dividing it by the number of grid points, and we have taken a root. So root mean, and we have a square of the Rij. So that is the reason it is called as root mean square. There are many ways you can stop the criteria. This is the one which is followed. So how I can now write is that, so at the beginning of the sweep, in case of computer program, at the beginning of the sweep, you will have to define some variable, sum is equals to 0, and then sweep for Rij, and Tij n plus 1, okay, and write sum is equals to sum plus Rij square, and end of sweep can be done, end of sweep is done by in RRMS, residual RMS is equals to sum divided by n points. Okay. You understand how to get this sum Rij? So you have to first initialize sum is equals to 0. That value will be keep on adding. Ri square will be adding. Okay. So this is a formula for adding Ri square values. So Ri square is now in some variable. So you write square root. So there will be a function in specific C. There will be sqrt or power function. which you can use to get the value of RRMS and see if RRMS, if RRMS, if RRMS is greater than epsilon, means we have not reached the solution. So go to the beginning of the sweep, go to the beginning of the sweep, go to the beginning of the sweep, else solution has conversed. Okay, if that is not the case, means else solution has conversed. Else solution has conversed. Solution has conversed, and the final values of Tij n plus 1 are accepted as the solution, accepted as the solution. So you see, in all this, you haven't constructed a matrix. Okay, so that is the reason this is called as matrix-free method, and this is mostly used in all CFD. Okay, solvers. So it is like this. So we've seen that in Gauss-Jordan, we simply do like that. So if I have to write, then for Gauss-Jordan, how much time do you have? How much time do you have?
Sir,
Sir, 5
around
minutes.
5 minutes, sir.
Okay, so I'll just write and stop. So we have beginning of sweep. And then we find Rij. Okay, Rij using that equations, using interior and bound, using equation for interior points, interior plus boundary points or boundaries, and sweep the value of Tij n plus 1. Okay, simply find out Rij and find out the Tij. To find out Tij, you should know Aii. Ai is already known. Okay, that will be known because Ai is nothing but 1 plus 2 gamma. Gamma x is nothing but alpha delta t delta x square. So delta t will be known, delta x will be known, alpha, these will be properties, k, rho, Cp will be given. So those everything will be known. So Tij you find out, then correct, then correct, then correct all Tij. Okay. Find first, correction means Tij is equals to Tij plus Rij divided by Ai. That is nothing using Tij n plus 1 is equals to Tij n plus 1 plus Rij divided by Ai. Okay, that is how you do. And in Gauss-Seidel, you do in a similar manner. Okay, but there is only one difference, is that beginning of sweep beginning of sweep is same, and we find Rij, okay, using that equation, then correct Tij, okay, n plus 1, and then you have to repeat this 1 and 2. If I write this 1 and 2 and this 3, repeat 1 and 2 for all grid points, So this difference is coming because we wanted to take the new values of gases, latest gas values. Okay. So in order to accommodate that, we are taking this. And we know from our exam question also, Gauss-Seidel method is fastest compared to Gauss-Jordan method. Same thing, what you may not be knowing is Gauss-Seidel method. So one important note is Gauss-Seidel method takes less memory. Why? Why it is taking less memory? Can anybody explain?
Rate of convergence is faster, sir.
Okay, but how rate of convergence is connected to memory?
Number of iterations will be less.
Okay,
So
but
the
connected
Sir,
to again connected to memory. How you can connect to memory compared to Gauss-Jordan?
sir, we are considering uh, latest gas value every time. So
Then, so how it is connected to memory? How will store the latest values or any old values? In terms of array. Okay, in terms of array. Okay. So, so the arrays required for creating the, these storing these values will be more in case of Gauss-Jordan as compared to Gauss-Seidel. So by storing the latest value, it essentially saves the memory. Okay. Okay, very good. Okay, then we'll stop. We'll see in the next class the application of this Gauss-Seidel to BTCS method in tomorrow's class. Thank you.